And so what I'd like to do, and this is an interesting time when we have to make all these presentations in WebEx. In some ways, it's actually kind of good that I didn't have to travel all the way. But then again, it's so much better to be able to talk in front of an audience. So I mean, certainly when when I'm talking to the machine, I tend to go fast. So in case if you have any questions, feel free to stop me and ask questions. So what I'd like to do is talk about some of the work that we've been doing on re-engineering computing with neuro-inspired learning. And so I'm going to talk about algorithms, architecture, and possible neuromimetic devices that can potentially give you improvements in terms of some of the neuro-inspired learning that I'm going to be talking about. Before I get started, I'd like to really acknowledge my contributors and my students. Where some of them are at Purdue and some of them are Purdue alumni at the moment. And they're really the heart and soul, and they make all these things happen, and I get to talk about their work. So with that in mind, let me just try to move one thing. All right. All right, so we've all heard of deep learning these days. And so if you look at deep learning and AI, that is certainly scaling across different applications. And these applications certainly include, image analytics, media, medicine, security, you name it. And if you to really look at, let me see if I got stuck here now. Let me see if I can do something. The slide is not moving, so I'm trying to see if I can. I hope I don't have to reboot it or anything.
I don't know if maybe you're able to close down the presentation and open it back up again, or.
Yeah, that's what I was trying. Let's skip now. Let's see. Yeah. So as I said, okay, seems to be working. So with, as I mentioned, AI is scaling across applications, across investments and people. And if you look at the slide at the bottom, which really shows the growth of AI in terms of the number of papers which are being published, the course enrollment, the VC funding, and so on, we actually see skyrocketing. And as an example, if you really look at the, certainly number of papers published in major conferences that going up like crazy. But on the other side of it, if you really think about the course enrollment, today if we have any course with an AI or machine learning or neural networks in it, the course enrollments are way higher than what it used to be. More than 200 to 300 graduate students enrolling in some of these courses. So with that in mind, certainly there are several challenges yet to be addressed. And some of these challenges, as an example, chatbots lead to about 80% cell decline. And that's something that, you might have noticed. Another area which is also quite important, and, we all have a good amount of problems with it, is, explainability in AI. Sometimes we don't know why things work, and sometimes we don't know why things don't work. So AI is like a black box. So there's a need for really, going into the black box and understanding the black box, and that requires a good amount of mathematical understanding of what's going on. And we'll talk a little bit about malevolent machine learning, and security turns out it's almost an issue, and especially with adversarial inputs that I'm going to be talking about briefly a little later on. And certainly consumer concerns, and these are some of the concerns that consumers have about self-driving cars. To start with 50% thinking that they would be. Now, how about a compute demand? It turns out, and if we really look at training, and training is requires a huge number of operations. And what I'm showing here is I'm plotting zeta operations on the x-axis, y-axis, and the x-axis being time. And what you really see is that for image classification, language processing, and I'm going to take an example of NAS, which is network architecture synthesis. It turns out that a number of huge number of operations is required. if I were to translate that in terms of carbon emission, what you really see is that carbon emission from NAS on transformer, which is a big neural network, is about 315x higher than air travel from New York to San Francisco per passenger, or about 5 times higher than the lifetime of a car. So these are really, really huge numbers in energy consumption. And on the other side of it, if you really look at, for example, the energy efficiency gap in AI, and this is actually for inference that I'm talking about, we did a case study on object recognition on a smart glass with state-of-the-art accelerator. In this particular case, the state-of-the-art accelerator with Google HTPU on a smart glass, and I'm showing an example of a flight attendant in this particular case actually recognizing very important customers using this smart glass. And doing an analysis of it, it turns out that we did an analysis of implementing, a retina net, which is object recognition on smart glass. And if you do an analysis of it with a standard battery, turns out that the battery life is going to be, for this example, is going to be about 1 hour under ideal conditions. So if you really consider the fact that under normal conditions, which is not ideal, the battery life is going to be about half an hour. So the question then, of course, is where do these inefficiencies come from? And that's what I'm going to be trying to address, later on in the talk, is that some of these inefficiencies do come from the algorithms, not having the right kind of hardware architecture, and certainly not having the right kind of circuits and devices that can mimic the neuron. Now, beyond compute efficiency, and I'm not going to be focusing today on that too much, is the fact that when it comes to AI, there's a need for learning, and today we need a humongous amount of data to learn. So the question, of course, is can I learn with less data? And the other side of it, there are other problems that one has to face, facing problems of generalization and robustness. As an example of generalization, if my system learns, for example, this at the chair, the question then obviously comes up is that, hey, would my system be able to generalize to assuming the pictures that I'm showing below, whether they are chairs or not, and in fact they're chairs based on the features and of course the context of where it is. How about robustness? Interestingly, you might have seen some of these earlier. If I really show my system as an example, this Macau, which is I'm showing on the left, and with high confidence, my system would say that, hey, it's a Macau. However, if I end up adding a noise, and this is actually a crafted noise or adversarial perturbation that I do, it turns out that the image to your naked eye is certainly not going to look the same. There is no difference at all, and you would still, as a human being, say that it's a Macau. However, the same image now, when I show it to my system as an example, it probably gives with a very high confidence, almost 90% confidence, that's a bookcase. So why does that happen? There's several reasons behind it, and there's a lot of work which is going on in some of these adversarial robustness. But what I really wanted to bring forth is the fact that robustness is a huge issue that one has to deal with. And on the other side of it, a few other things, which I'm not going to be again talking much about, is lifelong learning. So we as human beings are really good at learning over time. We don't forget tasks that are important, and we keep on learning. However, today's systems, if I learn, makes a network learn, for example, task 1, followed by task 2, followed by task 3, it turns out it ends up forgetting, task 1, task 2, and it ends up remembering only task 2. In order to learn, then what you really have to do is you have to mix up, task 1, task 2, and task 3, and then relearn all those sort of things again to be able to actually remember, all the 3. So that's a big problem. And to that effect, there's a huge amount of work which is focused today on, lifelong learning or incremental. Now, so there's a need for really thinking about, in order to address some of these problems, there's a need to think about the next generation of AI systems. So the design of these next generation AI systems can potentially happen, and that's what we are focusing on as a part of our center, which is the Center for Brain-Inspired Computing, is by drawing from neuroscience, drawing from mathematical foundations that we know about, and using, CMOS and beyond CMOS strategies. So just to give you an example of it, for the next generation AI systems, one can take cues from neuroscience. So what kind of network topology that we need to use? What kind of information representation, and that's what I'm going to be focusing on. What kind of information representation turns out to be important? What kind of learning model is important? Okay, these are the things that I'm going to be focusing on. But on the other side of it, there's a need to also, open the black box, the AI black box that we have. And opening the black box, as I mentioned earlier, that sometimes we don't know why things work and why things don't work in certain cases. The question, of course, is can I use mathematical theories and foundations and use theory of learning, network optimization, and more importantly, would I be able to do safety and robustness analysis? And finally, I'll briefly talk about some of these things. Is that hey, can I use beyond CMOS and beyond CMOS fabric to be able to actually utilize these devices in an effective way as neurons and synapses using a single device? Can I do in-memory computing? As an example, we all know that brain doesn't look like a standard von-Neumann machine. We don't really have on one side of our brain the memory, on the other side of it processing unit and the community. In some interesting ways, what brain does is it does computation on memory itself using very interesting computing fabrics, which in some cases we don't understand fully well. So the question, of course, is that can I use some of these neuromimetic devices and use computing memory to effectively implement some of these new algorithms which are brain responsive. So with that in mind, what I'm going to be focusing on now is more on some of those next generation AI systems, looking at the network topology, information representation, and the learning model. So can I take cues from the brain? As an example, certainly I can try to use different neuron models, and in general, when you look at deep learning today, they mainly focus on a neuron model to have an activation function like a ReLU, in some cases a sigmoid. But the question is it possible to use more bioplausible models like stochastic neurons or integrate or nuclear integrate and fine neurons? The reason why sometimes we'd like to use some of these interesting models is because of the fact that we know that we have an existential proof that brain is quite efficient, and if we can use some of these models, is it possible to get better learning, more energy efficiency, and so on. So bioplausibility is really nothing other than a means to an end to achieving better learning, more energy efficient learning. How about the learning algorithms? Some of you might have heard of backpropagation learning. Is it the most effective way of learning? Still, what we have so far is most of the learning is done using backpropagation. Is it possible to do more bio-inspired learning like spike timing dependent plasticity, which is a localized learning combined? Can I combine some of these things together into a more efficient learning algorithm? On the other side of it, network topology, which I'm not going to talk a lot about, is should I have long-range connections? Should I have feedback connections, and so on? And finally, using the computing principles of brain, what kind of computing and communication should I have? Should I have the communication with spikes? And that's what I'm going to be focusing on mainly in the next part of the talk. Should I have a tightly integrated compute and memory? The architecture be asynchronous, event-driven, and what kind of input coding should I use? Should I be using time-based coding, rate coding, and so on? So with that in mind, I'm going to just briefly talk about some of the neuron models that one can potentially look at. And this is actually a spiking neuron model. Coming from the biological, neuron synaptic models, one can potentially use a spiking neuron model. The basic idea is that the input spike comes from the neuron to the post neuron, and the membrane potential of these neurons goes up. And then if there are no spikes coming, it decays. And beyond a certain point, when a large number of spikes come, the neuron fires. And then after the firing, it's reset, and again, the same operation. So it's usually represented in terms of a integrated fire model, which is basically shown by this. And that's a more bioplausible model. So that's what however, if you really look at an integrated fire neuron as opposed to an integrated fire neuron, that doesn't have the nuclear part to it. And as you can see, that an integrated fire neuron is possibly can have a little more switching than missing integrated binary. So what are the advantages and disadvantages of each? I'm not going to go into the details of it, but there's a lot of work which is going on trying to show that, hey, some of these liquid behavior can have better generalization capability. But on the other side of it, one can also think of a stochastic neuron. Here, some of these, we see later on, some of these devices have this, behavior, interesting behavior where the switching is stochastic in nature. And if you look at the switching behavior of some of these devices, they show that there's a probability of switching associated with them, and that they look like a sigmoid. Then the question, of course, is, hey, since the switching behavior is sigmoid in nature, can I represent my neuron using a stochastic sigmoid? And it turns out if you do that, you can actually get a huge amount of model compressions and all, and we'll see later on that you can potentially get neural networks which are quite efficient and efficient in terms of memory and can potentially have better generalization. So now how about the synapses? So if I have to really look at more of a biosynaptic, bioplausible model, it has been observed back in 1998 in the hippocampus of rats, something called this kind of learning, which is called spike timing dependent plasticity. If I have to really look at a bunch of input neurons which are given by I1, I2, and I3, and an output neuron O1, if the input neuron spikes at a certain time that I'm showing here, and the output neuron spikes, the basic thinking is that, hey, since I3 is spiking, closer to 1, then of course that is more related to that. And that's what actually Wu and Pai back in 1998, when we looked at the hippocampus of rats, that's what they found. In fact, interestingly enough, what they found is that the synaptic plasticity of W3 is dependent on the time difference between when the input spikes at I3 versus the output spiking at 1. And similarly, I mean, I1 is also associated with some, the output spiking activity, but that's related less than, W3. So with that in mind, what they observed is that spike timing plays an important role, and the synaptic plasticity depends on, the difference between the output spiking and the input spiking. So that weight update rule in that case is really dependent on, the new weight is going to be dependent on when the output was spiking versus the input. And that rule is a localized learning rule. They don't have to go all the way to the output to determine what the input spike or weight should be. And that's a good rule. However, and it can be used in unsupervised learning, but still people haven't really been able to get a huge amount of accuracy, localized learning. Now, on the other side of it, of course, this is the synaptic plasticity, but also it turns out that you can have depression and of the synaptic weights are based on if you realize that, hey, the input that is coming in and the output are not correlated at all, then I'd like to do so. And that's basically the synaptic learning rule that's been used in those slides. But on the other side of it, on the left, I'm showing what the standard, deep learning technique, learning rules are. They actually use back propagation, so you forward propagate, your input, and you look at the loss function of output, and based on the loss function, you back propagate and determine what the weight should be. So this is actually, using stochastic gradient descent, and it turns out mathematically that has been shown to work pretty well. And most of the, deep learning scenarios they use in deep learning cases, they use back propagation. It takes a humongous amount of time, but that's, one of the techniques that we use. Now the question, of course, is can I use it in spiking neurons? We'll see that one has to make some adjustments to use it in, spiking neural networks. So with such, neuronal and synaptic learning that I just talked about, the question is, can I get some improvement compared to the standard deep learning framework that we're all used to? So there are three research fronts that one can look at in some of these bioplausible spiking neural networks. One is sparsity, and that's something that we'll go into a lot more details of when we find that sparsity can potentially be energy efficiency. On the other side of it, I briefly talked about stochastic, neurons. And stochasticity actually turns out it can give you weight efficiency or weight compression, and that's quite useful in terms of energy efficiency also. And finally, the temporality, and that has not been used very effectively, but in order to design dynamical systems, the temporal information as to when spikes come in and the spike timing difference, that can potentially play a very, very important role in learning. We don't know how to effectively use it yet, but I will give you some of the examples of these temporalities, and that can potentially give you efficient dynamical systems. So with that in mind, what I'm going to try to do is look at sparsity first and look at how to train some of these spiking neurons. How do you efficiently train some of these spiking neurons? To date, there hasn't been, more recently, there's a good amount of work started in training these spiking neural networks. And to date, there's been a good amount of improvement that have been observed, and efficient design of neural networks, spiking neural networks. So one of the easiest way of training is to take a standard deep learning ANN. I'm going to call these ANNs to be, rather than artificial neural networks, I'm going to call them to be analog neural networks, because the inputs are all analog in nature rather than spikes, which are 1, 0 kind of. So if you take a trained, trained ANN, the question, of course, is can I convert it into an SNN? And so the question is, how do you convert? Because in ANN, which is I'm showing on the left, basically they use the rectified linear unit. On the right side of it, I'm showing an integrated fire neuron, which is basically using the kind of membrane potential of the activation function that I talked about. So how do I really compare that? It turns out value is certainly related to the integrated fire neuron, not so much to this integrated fire neuron, but just to the integrated fire neuron. But what we really have to make sure that when the input come in, and if the input is 0.5 on my ANN, my expected value of my input should be 0.5 on the spiking neural. This is basically my ReLU, which is basically used as the output is basically max of, if I have to use a weight of 0.5, I'm using this function. On the other side of it, I'd like my expected value of the output to be also 0.25 in case of a spiking neuron, if I were to use my weight to be. But remember, what really the major difference is that on the left side, I don't have a threshold. On the right side, I have a threshold. And the threshold really comes from the integrated fire neuron. When I reach the threshold, I have spiking, and it's reset to a value. So with that in mind, we actually have we need a way of somehow balancing the threshold so that I come up with a proper threshold for my spiking neural network. If my threshold is too low, I'm going to be getting a lot of spiking. If my threshold is too high, I'm going to have hardly any spiking. So with that in mind, the answer lies in properly balancing. I'm not going to go into the details of the algorithm of balancing the threshold, but I'm going to show you some results. Where what we found is that after converting an N into SNN, one can potentially get a good amount of improvement in energy. The question, of course, is, first of all, I have to really look at what kind of, what kind of accuracy I get. So most of these cases, we look at VGG16 or a ResNet 34, look at ImageNet, and what we found is that, the ImageNet accuracy or the 2x10 accuracy were quite similar, a little bit lower, but quite similar to the ANN accuracy after conversion. But what is also important to note is the fact that if I were to really look at VGG16 and this ResNet 34, implementing actually in this particular case, ImageNet, what we found is that sparsity increases with depth, as I'm showing on the right, the number of layers versus the total number of spikes per neuron in the later layers is very, very low, and sparsity actually improves energy consumption. So to really think about having a spiking neural network, and if you have enough sparsity and even driven computation, you can potentially get a large improvement compared to what you get in an ANN. However, life is not that simple. The number of time steps required to do these computations actually is quite large using these ANN to SNN conversions. The number of time steps required in this particular case, which is related to the latency, turns out to be of the order of about 1,000 to 2,000. So that's bad. So we don't want it. So the question, of course, is, hey, can I improve it? So one way of improving it, because I didn't really train it as a spiking neural network circuit, I really trained it as an standard ANN and converted it. It turns out that a better way of training would be, if I were to train using, back propagation. And back propagation in the spiking domain as opposed to the analog domain. In analog domain, things are a lot simpler because the activation function that I'm talking about, and people use ReLU, or for example, sigmoid, and sigmoid and ReLU are differentiable. And that is a requirement when it comes to, back propagation. You need to be able to differentiate the activation functions and some of the, input and output spikes that are going to come in. So there's a need for that, and you have to make some approximations. So what are these approximations that you need to make? So you have a leaking, and by the way, in this particular case, I don't have to have an integrated fired neuron. I can use a leaky integrated fired neuron, which is not plausible. And but I have to do some approximations when I do the back propagation. Or in other words, what I really need to do is that I need to think about looking at the activation function, and in order to back propagate to my circuit, I need to make an approximation to my neuron. There are several ways of doing these approximations. Approximation of spikes. You can approximate the spikes as a two linear function, or you can approximate a spike using an exponential function, and similarly you can do various kinds of approximations. I'm not going to go into some of these surrogate gradient techniques, but what I'm going to try to show is that, hey, back propagation using such techniques is possible. It takes a long time, and the reason why it takes a long time is that I can potentially think of my inputs this time not as an analog input, but as a Poisson spike trend that comes in. And each of those Poisson spike trends for an image, for example, is going to be represented each pixel using a bunch of these spikes, which are generated using a Poisson spike trend. And then it goes to the deeply integrated fired neuron. And finally, you get the output. However, in order to do back propagation now, what you really have to do is for propagation, go through these different steps. And in the back propagation, you have to now unroll the network in time and then do the back propagation. So not only you have to do those surrogate gradient techniques, those approximations, but you also approximate, unroll the network in time and do the back propagation. And that becomes quite expensive in terms of time, and if you want to implement that in a GPU, that takes a long. But there's other ways of doing it. I'm going to briefly mention that in a minute. But what we found is that if you really do the back propagation directly in the spiking domain, we are able to actually use, VGG9 as an example. Difficult to use it for very large scale networks because that takes a long, long time. But this is basically showing that if you can try to compare that with a converted and new method of generating these SNMs, what we found is that the best accuracy, you don't need thousands of time steps anymore. You can do with hundreds of time steps, which is way better than what I showed you. So in other words, less number of time steps, hence my inference speed up increases under IC accuracy for this particular case, 2/10. And again, at the same time, what we found is that due to that, my energy efficiency also. These are some of the results on C/10, and what we found again is offers about 6 to 15x improvement in compute efficiency compared to the standard ANN. I must also admit that these values represent the synaptic compute energy and memory energy usage and the activation computation. This is basically just the compute energy compared to, for example, an SNN and a converted SNN. So yes, it's possible, but difficulty lies in the cons are of course higher training. Now on the other side of it, can I take a hybrid approach? And that can make things way better. The hybrid approach is I take an ANN to SNN and I take an ANN, and then what I do is I convert it into an SNN, and then after that I do a spike-based back propagation. The spike-based back propagation is done as an incremental step. I take an n into Sn and converted one. Then I do some incremental backpropagation with spikes. And this is actually we did very recently. And what we found is that it can give you a good amount of improvement. This is actually going to appear at ICLR again, just like any other conference these days. It's all going to be virtual. But the idea is that you can take a converted n into SNN, then use incremental backpropagation on it, so that it don't take much time. And what we found is that, again, quickly going over some of these results, it shows that you can start with an n into SNN converted network, from n and you convert it, and then actually do a simple n into n conversion, reduce the number of time steps required to, let's say, 2,500 to 250, and then you retrain some of these using spike-based backpropagation to get your accuracy. And that can potentially be quite useful. And now, as you can see, we can do it on ImageNet and other large networks, not only CPR10, but also on ImageNet and also on ResNet and other kinds of. With that in mind, I'm going to change gear a little bit and very quickly talk about stochasticity and temporality. If I do really look at stochasticity, as I mentioned earlier, that we can now look at learning and learning to do stochastic imaging. Now, when I say learning is stochastic, when you learn it is stochastic, but the synapses are going to not remain stochastic when you do inference. During inference time, of course, there is not going to be any stochastic. I can have stochastic in my neuron, but not on my synapse. So the question is, how do I do the training? One can potentially think of and input with a convolutional neural network, where convolutions are the feature extractors. And then what you do, the training in this particular case is not backpropagation, but let's say we do localized training, like what I briefly talked about earlier on, using spike timing dependent plasticity. So what was spike timing dependent plasticity learning? The basic idea was that, hey, I'm going to look at the output spikes and the input spikes of a neuron, and based on the input and output spikes, I'm going to determine how much I'm going to potentiate or depress my synaptic weight. So earlier, what I did is I looked at the T-pre, which is the pre-neuron spiking time, T-post, which is the post-neuron spiking time, which is the localized learning, and based on that, I updated my W with a delta W. So in this particular case, I'm not going to do delta W. I'm going to do a P delta W, probability that a particular weight is going to remain at 0 or equal to 1. And that is related to the change that I'm going to have, T3 minus. So rather than delta W, I'm replacing it with a probability of delta W. And we'll see later on that can directly translate into the devices that I use. So the last layer, now in this particular case, is going to be a fully connected layer, and the fully connected layer now is going to be trained using a back propagation only up to the box that I'm showing. So after that, fully connected layer, I have the animals, monuments, birds, whatever I'm doing. So we did that. We found that, hey, the number of spikes, as I mentioned earlier, would decrease as we have more and more, layers, convolution layers. So we ended up adding what I call stick connections, or residual connections. So these residual connections now can make my network, better trainable. And with that in mind, actually, I'm showing some results on, stochastic training with stochastic STD. People haven't really been able to show it on, anything other than CPR10, and this is really our good showing that it's possible to do this kind of learning, and which is fast, efficient because of the localized learning. It's actually quite fast, and can potentially be used in edge devices. Accuracy, certainly not as good as we have in an ANN, but again, good enough to be used in possibly edge devices for energy efficiency. Finally, dynamical systems, and as I mentioned, we didn't really use temporality in a very, very effective way earlier. So the question, of course, is it possible that I use temporal information? How does the input come in? If the spike come in at a particular time, and it's very important to use that timing information. Most of the time, in a standard ANN, we never use that timing information in computational. So to that effect, we wanted to take an example of something that we'd like to do, for example, beyond perception. So far, I've talked about perception, applications. But is it possible that I do go beyond perception and look at motor pattern generation? So as an example, what is the motor pattern generation? I'm going to take an example of what has been observed again in the humans, and this was some experiments done in UCLA, and based on that, we're looking at the motor pattern generation, where the idea is that I'm basically asking my network, in voice, to say, hey, write 1, write 2, write A, write B. So the basic idea is that I'm going to take this input and taking the voice as different input signals in terms of frequency that is going to be fed into my network, and this network now is going to go into some interesting patterns after I train them into some attractive states, and these attractive states help in learning, or at least doing some motor patterns like the network at the end of it, end up writing 1 or 2 or 3 and so on. So with that, and the output neuron can be 2 output neurons. One is for the X direction, another is for the Y direction, and that can move in such a way that it can go. So this is an example. I'm not going to go into the details of training this network, but the idea is to use very, very simple-minded network. And what I'm showing here is a Neuro-Inspired neuron with a bunch of random neurons connected together. They're connected in a random fashion with backward connections and so on. And the backward connections are important. The residual or the recurrent connections are important because you need to store information about the voice in some way, and then be able to reproduce what the voice says in terms of writing. So just to give you an example of it, what we did is we actually trained the network. I'm going to skip the different training steps, but what I'd like to show is that with the voice commands now, the network initially goes takes the input and then goes into these extractive states, and each of them is going to go into different extractive states depending on the input that comes in. And now the output neurons, which are moving in X and Y direction and doing this motor function, sort of ends up writing into writing the input, writing as an output with the voice command. So these are some of the things that one can do. One can also use such a network again with DVS cameras, where some of you might be familiar with DVS cameras. These cameras are actually kind of interesting. They take inputs, and if nothing is moving in the scene, they don't actually don't produce an output. But if there's something moving, they basically provide the pixels which are moving, and those are going to be in terms of size. So you take this input data, which are very suitable for a spiking neural network, and very energy efficient because we only send the spikes when there is an activity of input. And using that, one can potentially have various kinds of these spiking neural networks. In this particular case, I'm showing a very kind of network that I showed earlier on a random network, liquid state machine. And using that network, one can potentially use very simple commands in this particular case, the hand movement, going up, going down, and so on. And one of my students, as you can see in this particular case, is asking the robot, asking it to perform to the business camera, and asking the robot as a drone to go up, to go down, based on these hand movements, which is and it's a demo of all these things. You see there's a delay in it because this is a discrete system that we have developed, so you can actually go back and forth, move right, move left, and all kinds of things. Using devices material is very, very energy efficient because of the fact that we're using these kinds of false inputs, and the computation is being done using these cameras. And finally, I'm going to take just a few minutes just to show. I'm not going to talk about the mathematical foundations, but I thought that very quickly, since I talked about the devices, I thought that I'll just show you some of the device fabrics that I'm potentially.
Professor,
yeah.
We've got about 1 minute left.
Oh, okay. Yeah, I mean, I'm just not going to take much time, but just wanted to show these are the neuromimic devices. Devices can mimic the neurons and synapses. So wanted to show you a bunch of these colorful devices that one can use. In particular, actually, I'm showing RRAMs, CCRAMs, or magnetic tunnel junctions, and showing again that if you look at a biological neuron, and a magnetic thermal junction, what I'm really showing is that they actually are equivalent in some ways. The magnetization dynamics with spikes look exactly similar to a spiking or lift integrated inside neuron. And to that effect, you can also design a stochastic neuron using such devices. Remember, I showed a stochastic sigmoid function that can be done, and this is actually the fabricated device which shows that kind of behavior. And using these devices, one can potentially think of developing spiking neural networks, which can be really compact, can do in-memory computing. I know that I didn't talk much about in-memory computing part of it, but one can do in-memory computing and can implement it, these networks in a tiled architecture that we developed, ReachPark, and showing that some of these energy analysis. So I'm going to, end the talk with a summary that I talked about NN to SNN conversion, backpropagation in SNN, possible energy efficiency improvements, can be quite large compared to the NN. We looked at SPGC learning. What we feel is that such learning would end up doing reasonable clustering, but can be applicable to small cell networks. To that, I always say ImageNet is not everything, can certainly be useful for edge devices. And we also looked at the liquid set machine for speech, video, and so on. It's kind of like an universal architecture that captures the multiple. Where do SNN see energy efficiency, potential for edge computing, emerging devices that can potentially harness the synapse and neuron functionality. And I personally believe that temporal domain is key. We need to effectively use them to be able to see the real benefits of the architecture. So hardware co-design, algorithm hardware co-design, yep. These are my students who actually make things happen. And I'd also like to acknowledge our sponsors, the Center for Neuro-Inspired Learning, fellows, and other funding agencies. Thank you very much.
Thank you. Thank you very much, Professor. We're going to go ahead and skip the Q&A session, go right to the Best Paper Awards.
Sure.
So, Kurt, do you want to go ahead and take it over?